you can see that this molecule has a negative charge on the carbon. Now that means there must be a lone pair of electrons there. I put it in brackets for now, but very soon I won't be drawing the lone pair, but I will always be giving you, for example, a negative charge. Well, we are looking at resonance structure and resonance form again, and hopefully things are starting to look a little bit familiar. That's because we've seen some very similar mechanisms. Let's replace the atoms for a moment with numbers to try to see a more generic nature to the mechanism. 1, 2, 3 could be oxygen, nitrogen, oxygen, or it could be oxygen, carbon, oxygen, or even carbon, carbon, oxygen. Whichever of these you want to look at, the mechanism is very, very similar, with arrows moving in an identical manner. This is a good way to think about mechanism. It can be very daunting to think, well, there are 150, maybe even 200 mechanisms you need to know. And I would encourage you to think more like that there are a couple of patterns of arrow movement that make up interchangeable sequences. And you can change the atoms and you can change the bonds, but the arrows tend to move in very similar ways. When you think like that, this very daunting range of mechanisms starts to get reduced down to a manageable number. So we're looking at a carbanion, a negative charge on a carbon. The arrow starts on the negative charge that on this carbon would imply a lone pair of electrons, and moves to the center of the single bond that results in it becoming a double bond. The second arrow starts in the middle of the second bond that's a double bond and goes on to the oxygen, and thus the second bond goes from being a double bond to a single bond, and the oxygen goes from being neutral to negative with an extra lone pair of electrons implied on the oxygen. This produces an enolate. So far, by and large, we have seen 3 atoms being involved in creating resonance structure, with the exception of benzene. But let's take a look now at a 5-atom system. Here we can see we have oxygen, carbon, carbon system. Very similar to what we just saw. But if we continue, we have another carbon and another oxygen. So the mechanism starts out identical to the last example. The negative charge starts the arrow that ends in the middle of the single bond, and then the second arrow starts in the middle of the double bond and ends on the oxygen, creating a negative charge on the oxygen. Because of the negative charge, an extra lone pair is present beyond those found in the neutral species. But it's not depicted here, as I want you to get used to it being implied. Now something new happens. The arrow starts on the oxygen, and with a sequence of 3 arrows, an arrow ends on the other oxygen. What we have achieved is 3 resonance structures. So how does this compare with the earlier example of the enolate? Well, the enolate produces 2 resonance structures, and the charge is spread over 3 atoms. This is less stable than the new case, where we have 3 resonance structures and the charge is spread over 5 atoms. So this 1,3-dicarbonyl system is more stable than the enolate example. So in our generic mechanism, we've seen oxygen, nitrogen, oxygen, oxygen, carbon, oxygen, carbon, carbon, oxygen, and we're going to finish off with carbon, carbon, carbon. So, looking carefully again, it's the same mechanism. You're beginning to get comfortable, hopefully, with this specific manner in which arrows move. This is called an allylic anion. But you can see we still have a carbanion at the start of the first arrow. So thus far we've seen how a negative charge is used with arrow movement. What happens if there's a positive charge? Well, here's an example of an allylic cation. This involves a carbocation. Now we have 3 atoms, but notice that because we're not dealing with a negative charge and we are dealing with a positive charge, the arrows that are moving are different. We have one arrow that starts in the middle of the first bond, that's a double bond, and ends in the middle of the second bond, that's a single bond. Thus, the double bond becomes a single bond, and the single bond becomes a double bond. And notice the positive charge moves between the terminal carbons. What about a molecule that involves both a positive charge and a negative charge? When 2 such charges exist on the same molecule, it's described as an ylide. When we want to describe a nitrogen version of a system that has a non-nitrogen analog, this can be indicated by the term aza. Thus, this particular type of ylide is described as an aza-ylide. This specific functionality is called an azide. The arrows move very much like the carbanion that we saw earlier. Here I'm showing you how to move backwards. So the resonance structures can either react forwards or backwards. The arrow movement is similar, but with different bond types involved.